So on the basis of the current state and the input symbol, it decides, makes a decision table, if you like, or transition table, same thing, what the next state should be. Alright? Okay, well let's, now you can list those transition rules in a transition table, state transition table, did that earlier session. Or you, now the rules are implicit, they're all here, all the information for your automaton is in your state diagram, which is short, remember, for state transition diagram. Here are the states, and here are your transitions, these arrows are the transitions. Now this arrow here, that's not a transition, that's your start arrow. Now you have to start somewhere, you have to start in one of the states. Okay, so you start, because we see this arrow, so we know you're starting in state Q1. You start there, right? And then the string, input string comes in, and you start reading the first symbol and the second and so on. So let's do it. So here's your start arrow, so you know you start in state Q1. Okay, start in state Q1. So you start here. Then you read the 1, and one of your transition rules will become active. And which one? Well, if Q1 and input symbol is 1, which it is, right? First one is a 1 here. So if state Q1 and input symbol is 1, then transition to state Q2. So you're now here. I'll put my finger in again. Okay. Now second symbol comes in. It's a 1. The second 1 here. You're in state Q2, and the input symbol is a 1. So you transition to, well, back to Q2. So in other words, you don't change the state. Well, or if you like, you transition to the new state that's the same as the current state. Well, the old state. Okay, so now you're in state Q2. And now 0 comes in, that's the third symbol. So if state Q2 and input symbol is 0, then transition to Q3. So now you're here. Right? And now the fourth symbol comes in. It's a 1 here. Right? So you're in state Q3. So if state Q3 and input symbol is a 1, transition to Q2. So you go along this transition, this arrow. So you're back here. That's the last symbol. Okay. So your final state now is Q2. But Q2 is an accept state. It's got a double circle. And therefore, this whole automaton, the whole thing, accepts this string. Okay? It accepts that string because the final state was one of, or was only one in this case, but was one of the accept states. Okay? Starting to get the hang of what an automaton does. Right? So that lists what I've just been saying. Okay? So you accept because M1, the machine, the automaton, is in an accept state, Q2, at the end of the input string. Right? Now that was just for one string, 1101. So, but you could input other strings, different strings, and in some cases the automaton, M1 will accept them. Other cases will reject them. So, the obvious question arises, well, all those strings that are accepted, in other words, the language, so create the set of all input strings that are accepted and call that set A. In other words, language A. I heard a ping. I think it was my computer, not. Yeah. Okay. I don't want to talk when I'm not being recorded. It's just a waste of time. So, my camcorder goes ping when the memory, but it's a similar sound to the computer. But I see the computer has finished doing something, so it's okay. All right. Okay. So, the obvious question arises. So all these strings that are in language A, in other words, all these strings that get accepted by the automaton, what do they have in common? So it's sort of like if you've done any artificial intelligence and machine learning, you could be given a whole bunch of strings that are accepted by the automaton and a whole bunch of strings that are not accepted, and then your machine learning program has to discover some rules about the strings that are accepted that differ from those that are not accepted. Right? So it's an interesting question. What do all these accepted strings have in common? In other words, this machine M1, just exactly what is it? What's the word? Recognizing? Yeah. What language is it recognizing? That's the technical term used in. You could say it accepts the language, but that's sort of ambiguous because you use the word accept for accepting a string. So let's use the word recognize, but it's essentially the same thing. And we'll come back to that point that I've just made in later sessions. Alright, okay, so now look, there's a whole bunch of strings that M1 accepts. Like, think this through for yourself. So if string 1, just one symbol goes in. So if the 1 goes in, so you get a transition to Q2 and then stops. Right? So the final state is Q2. So this string is accepted. Now how about 0, 1? Okay, 0, so it'll take you back to Q1, and then 1, take you to Q2. So your final state is an accept state. So 0, 1 is accepted. How about 1, 1? Okay, 1, 1, still in Q2, so accepted. And this much longer one, like 5 times 0, 1, so 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Well, let's do that. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, still in Q2. Right, so that's accepted. So you can do lots of examples, and you sort of come to the conclusion that M1 will accept any string that ends with 1. Okay, because when it reads a 1, it goes to Q2. And what is that? Well, let's say it's here and it reads a 1. It goes here. And if it's in Q2 and it reads a 1, it stays there. And if it's in Q3 and it reads a 1, it goes to Q2. Okay? So if your last symbol is a 1, ends up in Q2. The final state is Q2. Okay? So M1 accepts any string ending with a 1. Okay? But that's not it. There's this rule. It's a sort of an OR rule. It's this rule or. There's another way it can get accepted. It'll accept any string that ends with an even number of zeros after the last one. Okay? So let's say, so we've got a 1. Let's say we're here, and then an even number of zeros follows the last one. So an even number of zeros. So 1, 2, 3, 4, 5, 6, 7, 8. So as long as you've got an even number of zeros at the end, you'll end up back in Q2. So imagine you have a string or substring and it ends with 1, so therefore you'll be here, and then it's followed by an even number of zeros. Well, because it's an even number, 1, 2, 1, 2, 1, 2, 1, 2, it'll end up there. Okay, now deducing what the function of an automaton is, takes a bit of intelligence, right? You have to think about it. Okay. Right. So that's the function of this particular machine, right? It will accept any string that ends in 1, or any string that has an even number of zeros at the end after the last one. Okay. Now, in fact, we'll come back to this later. What the definition of the actual language that this automaton accepts, recognizes. Okay. Now, any string that's not accepted is rejected. Okay, so alright. Okay, now change the topic a little bit. Now we've got a fairly good idea of what an automaton is about. Now we're going to become sort of like lawyers, and we're going to write down a formal, strict, mathematical definition of what an automaton is. And you may ask, well, why? What's the point of doing that? Well, there are two main reasons. One is precision. Okay, so if you have a strict definition, then sort of quasi-ambiguous sort of questions, fringy sort of questions can get answered by the strictness of the definition. And the other major reason for having a formal definition, mathematical definition of an automaton, is notation that you can then use in the analysis and manipulating other automata, plural. Now, in a couple of sessions, we'll start doing a whole, can't say string, a whole batch, quite a few examples of finite automata, and we will use this formal definition to describe each one using the notation, the strict notation of this definition. Right? So that will be. So there are two main reasons, just summarising a bit, for having a formal definition of a finite automaton. One is precision, so very clear, and the other one is notation. So you can use that notation in the future for describing other automata. Okay, so